Now, what if the driver of the Ferrari 550 was cruising along and suddenly hit the brakes to stop because she saw a cat in the road? She skidded to a stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car so that she knew that her braking distance was 31 feet. So how fast was she going when she hit the brakes? So let's go back and figure out, look at our equation. We had d of s is equal to 0.03 s squared. Now the first part of the assignment, or of the task, they gave us the speed. Now they're giving us the distance. And we have to figure out this equation, okay? So if I have the distance, I plug that one in. And now I'm going to divide everything by 0.03. And get that that is equal to, let's see, 31 divided by 0.03. And we get 1033.33 is equal to s squared. And then we can square root both sides. And remember, when you square root both sides, you could get plus or minus, but since we're talking about speed, it's only going to be the positive. And when we take the square root of both sides, we get that s is equal to, let's see, second square, 32.15 miles per hour. Now, if she didn't see the cat until she was 15 feet away, what is the fastest speed she could be traveling? So now we have 15 is equal to 0.03 s squared. And how do we know that this is the equation? Well, if she's only 15 feet away, that means she only has 15 feet to stop. Okay, and we're going to figure out the fastest, or what's going to take her exactly 15 feet to stop. So 15 divided by 0.03. And then we'll take the square root of that, because we have s squared is equal to 500. Take the square root of both sides, and we get that s is equal to 22.36. So 22.4 miles per hour. So she can't go, well, she'd probably be safer to say can't go above 22 miles an hour if she wants to be able to stop from hitting something 15 feet away. Now, part of the job of a police officer is to investigate traffic accidents and determine what caused the accident and which driver was at fault. They measure the braking distance using skid marks and calculate the speed using mathematical relationships such as what we just have here, although they often use different formulas to account for the various factors such as road condition. Now let's go back to a Ferrari on a smooth, dry road surface since we know the relationship, which is this, d of s is equal to 0.03 s squared. Create a table that shows the speed of the car was traveling based on the braking distance. So, on this part of the task, we're dealing with, if they give us the distance, we need to figure out the speed, because that's often what a police officer has to work with. He has the end result, the accident. He can see how long your skid marks are, so he knows the distance and he has to figure out how fast you were traveling. So let's plug in some of the points. I know that if the distance was 31 feet, I was traveling 32.15 miles an hour. If the distance was 15 feet, I would be traveling 22.4 miles an hour. Let's do another one, 10. Okay, and I'm going to, if I was to plug that in, I'd have 10 is equal to 0.03 s squared. So come up here, 10 divided by 0.03, and then you take the square root. Oops. And you get 18.25. Now you could put more values if you would like, but I think that will suffice. And then number 7 says, write an equation of the function s of d that gives the speed of the car was traveling for the given braking distance. Now, if I was simply to look at this table, I would have a very hard time figuring out an equation based on this table, personally. But we have now solved 3 different values. We've plugged in d 3 different times and figured out what s was. Well, what did we do each time? We first divided it by 0.03 and then took the square root. We divided by 0.03, took the square root. Divided by 0.03, took the square root. So, every time we took the distance, divided it by 0.03, and took the square root. And that gave us our speed. We just came up with the equation. Okay, first you divide it by 0.03, and then you take the square root of your answer. And that would give us the speed based on the distance. So graph S of d and describe its features. So we can go ahead and plot a few of our points. Remember, this is going to be a square root function. So to graph it, I first went through and labeled the axes. Now the input, or the x-axis, is going to be my distance, and my output is going to be my speed, which is going to be the opposite of the graph we used on the first part of the task. And then I just went through and made every little tick mark too, and then I just didn't label every single one since it was getting too cluttered, and I did that for both of them. So it has a scale of 2. And I'm just going to start by plotting the points I know. If I go over 31, so it's going to be right about here, I'm going to go up 32. So 31, go up about 32. Just a little over 32. And if I go over 15, I'm going to go up 22. And if I go over 10, I'm going to go up 18. Just a little over 18. So I can connect these. And also you could plug in 0, and if you plug in 0, you'll get 0, so we know it'll go through there. And stop right there, considering we can't have a negative stopping distance, so it's going to stop right there. And now let's talk about its features. So its min is going to be 0, 0 for our context. Okay, and that's going to be, that would be the min even if it wasn't, because we could never have the square root, because we're not dealing with imaginary numbers right now. We're going to have the domain. It's going to be from 0 to infinity. The range is going to be from 0 to infinity, if we are thinking that we could just forever get faster and faster and faster. The x and y intercepts are going to be at 0, 0. So I'm just going to put the intercepts. Sorry, my little pen is not wanting to cooperate. Will be at 0, 0. And we are going to be increasing from 0 to infinity. Now, I know some people look like this and think, oh, well, it's not growing as fast. It's going at a decreasing rate. But that's still increasing. If you're going from left to right, it's still continually getting bigger. It's just getting bigger at a slower rate. So it's still increasing.